Hi, I'm Norman Wildberger. Today we're going to have a look at a very beautiful and interesting and important object in the history of mathematics, which is a regular tetrahedron. And here's a model of it. Relatively simple but lovely symmetrical object. 4 vertices, 6 edges, 4 faces, the regular tetrahedron. So this has implications in a lot of different directions, actually. So this thing can be generalized in a number of ways, and they're all going to be interesting for us. So certainly one way is that this is the simplest of the 5 Platonic solids. There are 5 objects that have the same kind of regularity as this one does, where the faces are all regular polygons and the whole thing is completely symmetrical with respect to every face, with respect to every edge, with respect to every vertex. So there are 5 of them, the Platonic solids. This is the simplest one. Another generalization is to just allow a distortion so that we get a more general tetrahedron. It's a 3-dimensional analog of a triangle in 2-dimensional space. And just as a triangle plays a fundamental role in understanding planar geometry, so a general tetrahedron plays a fundamental role in understanding 3-dimensional space and the geometry in which we live. So that's another important generalization. Another generalization is to go up in dimension and to realize that this is a 3-dimensional object, which is really one in a family of objects, starting with an equilateral triangle, then this thing, the regular tetrahedron, and then there's a sort of 4-dimensional regular tetrahedron and a 5-dimensional regular tetrahedron and so on. They're often called simplices. Okay? So that's another pleasant example of a generalization. So today we're going to look at the geometry of this regular tetrahedron, which is very pleasant and gives us a chance to apply our understanding of both planar affine trigonometry and projective or elliptic trigonometry. We're going to be combining both of them in understanding the 3-dimensional geometry of this simple but lovely object. There's an interesting distinction between the equilateral triangle in the plane and this regular tetrahedron in 3-dimensional space. The equilateral triangle in the plane doesn't actually precisely exist. So we can make models of it, of course, and pictures, but if we want to actually construct it exactly in the rational plane, we're not able to do so. That turns out to be not the case for the regular tetrahedron, and it's an interesting situation. So here we have 3-dimensional space, and in this 3-dimensional space we see a cube. And it's really the existence of this cube that allows us to assert the existence of a regular tetrahedron, because the regular tetrahedron is contained inside the cube. All right, so let's see if we orient this in the same way over here. So, okay, there is the top vertex right there, and the vertex O, which is the origin, is the one down here. And if you look at this thing up close, then you will see that this vertex here, which is the origin, together with these 3 vertices of the cube, they form inside them this regular tetrahedron with these 6 green edges. Okay, it's the same tetrahedron that we had over here. It's the same thing. Let's put it in the right same position. So there's sort of the same position as over here. So this makes it very easy to specify this tetrahedron completely using our basic framework for Cartesian geometry. Here's x-axis, y-axis, z-axis. The cube is such that the corners here are at positions 1, 1, 1 in the x, y, and z directions. And so these vertices A, B, and C have coordinates 1, 1, 0. 1 in this direction, 1 in this direction, 0 in the z direction for A. B is 0 in the x direction, 1 in the y, 1 in the z. And C is 0 in the y direction, 1 in the x, and 1 in the z. So we have very precise control over the 4 vertices. The origin, of course, is just 0, 0, 0. And this makes analysis of this situation actually quite simple. Because of its pleasant regular shape, the regular tetrahedron occurs in a number of different areas. But in particular, it's important in chemistry, where it represents the shape of a methane molecule, CH4, where we have a carbon atom surrounded by 4 hydrogen atoms, which are equally spaced, so that the 4 hydrogen atoms form a tetrahedron with this carbon atom in the center. So the chemists are particularly interested in the geometry of this kind of thing because in chemistry, the geometry of molecules has something to do with chemical properties. In particular, they're interested in this angle formed here by this bond with C atom, one arm to an H, another arm to another H. This forms an angle, and that angle is, well-known angle to chemists, 109.47 degrees approximately. This is the angle formed by 2 hydrogen atoms from the central carbon atom. And this number will play an interesting role for us, or actually the rational analog of this will play an interesting role. So if you're a chemist, you will probably learn something interesting about this configuration that maybe is a little bit new to you. All right, so let's have a look at our basic cube here with the tetrahedron inside it. So each of the sides of the cube has quadrants 1. And so we can easily see from Pythagoras that the sides of the tetrahedron all have quadrants q equals 2. For example, the quadrants from here to here has to be 2 because this is a right triangle with quadrants 1, so that has to be quadrants 2. So we have quadrants 2, 2, 2, and also these ones are also 2. All right, so if we look at just one face, let's say the face ABC, that's going to be an equilateral triangle, of course, because each of the quadrants is equal to 2. And let's just check that the spread here, which is going to be common to all of these vertices, is what we expect it to be. We can calculate this spread S, if we didn't know it already, by the cross law in this affine situation. So let's say we are looking at this spread S, then 2 plus 2 minus 2 all squared should be 4 times 2 times 2 times 1 minus S. That's the cross law in the affine situation. Basically the most fundamental law in planar rational trigonometry. But of course applied to this very special situation where we have all of the quadrants is happening to be 2. So things simplify very quickly. Over here we have 2 squared, which is 4. That 4 will cancel with that 4 there. So we'll get 1 minus S equals 1/4, and so S equals 3/4. And so the spread here, the common spread in this equilateral triangle is 3/4, which is just the rational analog of 60 degrees. In rational trigonometry, 3/4 plays the role of 60 degrees, or pi by 3. Okay, so we forget about pi by 3, we forget about 60 degrees. Now 3/4 is the essential God-given number that we want to associate to an equilateral triangle, the vertices there. They have spreads of 3/4. Okay, and we call this the face spread of the tetrahedron because that spread will occur in each of the 4 faces. So that's one face, there will be 3 such spreads, and each one of the faces, say this one here, will also have 3 spreads of 3/4. So there's lots of 3/4 around the 4 faces of this tetrahedron. So there we've applied some planar trigonometry to understand the geometry of the face of the tetrahedron. Now let's have a look at some projective trigonometry to understand what happens at a vertex of the tetrahedron. All right, so let's take our tetrahedron and have a look at it from one vertex, say the origin here. Okay, so if we're at the origin here and looking at this tetrahedron, well, there are 3 edges emanating out from the origin. That's exactly the kind of situation of what we say is an elliptic triangle. It's basically a projective situation where you have one point and you have 3 lines through that particular point. So those three lines, if we forget about the rest of the object, just these three lines together form an elliptic triangle. So we can call these edges OA, which is just little a, and OB and OC represented by little b and little c. So here's another picture of the same thing where we're concentrating on just the three edges emanating from O. These are three lines whose names as lines or projective points are little a, b, and c. Okay, so then this gives us an elliptic triangle, which we can draw like this. So these points then will be A, B, and C. We could probably label them. Call this A, and this B, and this C. So these are now points which are representing these projective 1 points, which are lines through the origin. Okay, so this elliptic triangle has some quantities associated to it. And the thing that we do know about this thing is that the spread here between this line and this line is 3/4. And that's what we're calling the projective quadrants, or just the quadrants in the elliptic sense, between these 2 points. So the projective quadrants between A and B is 3/4. And similarly between B and C, 3/4, and between C and A, 3/4. So as an elliptic triangle, it's also equilateral, but now the 3 quadrants are 3/4. These projective spreads here are physically the spreads between the associated faces formed here. So these 3 lines determine 3 faces, one there, one there, one there, and between any 2 of those faces there's going to be a spread, and that's what we call this capital S. Okay, so in the elliptic situation there's a projective cross law which basically controls the whole story, and it's a little bit more complicated than the affine situation, and here's what it looks like in this particular case. So we take one of these S's, we multiply by 3/4 and 3/4, so S times 3/4 squared, and then we subtract this quadrant, and this quadrant, add 2, square all of that. That should be equal to 4 times 1 minus 3/4, 1 minus 3/4, 1 minus 3/4. That's a quadratic equation then in this unknown capital S. Well, things are relatively simple because the algebra is pretty easy. We have minus 3/4 times 3, so it's minus 9/4 there plus 2, so that'll be altogether minus 1/4. Here we have a coefficient of 9 over 16 times S. All of that squared should equal, on the right here we have 4 times 1/4, 1/4, 1/4 for a total of 1/16. Okay, so this is not so hard to solve because this happens to be a perfect square. So 9s over 16 minus 1/4 either equals 1/4 or minus 1/4. In the case of minus 1/4, then the minus 1/4 will cancel and we'll just get s equals 0. In the case when we have a plus 1/4, then we'll get 9s over 16 equals 1/4 plus 1/4, which is a half. So then s will be 16 over 2 times 9, or 8/9. That is the value for the projective spread in this elliptic triangle. This is a very interesting number that appears, okay, and it's an intimate part of the geometry of a regular tetrahedron that really only becomes visible once you adopt this rational point of view. We are able to see the real values of things like quadrances and spreads instead of approximate values to real number approximations of things obtained with calculus or transcendental functions. Okay. So this then gives us the information that we want about the geometry of this tetrahedron. We now understand what the situation is at every vertex and what the situation is at every face. Now there's another way of looking at what this 8/9 stands for. So here's our tetrahedron again, and I'm identifying the center of the cube and the tetrahedron. So here's our cube again. So somewhere right in the middle is the center of the cube. And because that's the origin and these are all ones here, that center is going to have coordinates 1/2, 1/2, 1/2. Let's call it P. So there it is right in the middle there. Okay, that's the center of the cube. It's also the center of this regular tetrahedron. So now if we take the center and imagine drawing perpendicular lines from that center to the four faces of the tetrahedron. So here, for example, is one face. And imagine just drawing a perpendicular line, like an altitude, from our center to this face. Right, so then that's a normal to this face. And if we have an adjacent face, say that one there, then that's going to be a normal to that face. If we take this face here, then we're going to get a normal like this. If we take this face here, we get a normal like this. So these are the four normals to the four faces from the center point of our tetrahedron. Now, the spread between two faces of the tetrahedron is the same as the spread formed by the normals to those faces. Okay, so we've calculated the spreads between the two faces. It means that we've calculated the spreads between the two normals to those faces. So we can say that the spread between this normal and that normal is 8/9. In fact, the spread between any of these two faces will be 8/9. And so we see that what we're doing is we're recovering this angle formed by the methane molecule, except in a rational formulation here. This 8/9 is exactly the rational analog of this angle, 109.47 degrees, which is only an approximate value. And one can calculate that, yes indeed, if you take the sine squared of this angle, you get approximately 8/9. So yes, the 8/9 really is playing the more fundamental role about describing not just the regular tetrahedron, but also the geometry of the methane molecule. So chemists, you have now an alternate, perhaps better way of thinking about the geometry of the methane molecule, using some rational trigonometry instead of classical angular measurements. It's now an exact measurement, and it's connecting with a lot more things, and also has interesting generalizations to the other Platonic solids. So we can now ask, well, if we take one of the more complicated Platonic solids, like an octahedron or a dodecahedron or icosahedron, what kind of similar kinds of numbers are going to be appearing when we start asking questions about the geometry of these things? The geometry of the Platonic solids goes back to the ancient Greeks. It was a prime motivator to Euclid in establishing his entire book. The Elements sort of had the Platonic solids as a motivating example that he got to at the very end. So this question of what is the geometry of the classical Platonic solids is a very historically interesting and important question. We'll be able to say some new and more powerful things about it by pursuing this kind of direction. In our next video, I want to in fact show you how this number 8/9 appears in a quite different context, having to do with paper sizes. So in the US, we have 8.5 by 11 papers when you're writing, but in Australia, for example, we have A4 sheets of paper. And I want to talk a little bit about paper sizes, and we'll see that, perhaps a little bit surprisingly, this number 8/9 occurs naturally in the A series of paper sizes. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.